Hi everybody, we'll continue the presentations in this course of Calculus 1. Now with chapter 4, application of differentiation. And the first section is about the maximum and minimum values. It's not that difficult, but there are many details to keep in mind and to understand what the critical value is, what absolute minimum, absolute maximum, local minimum, local maximum. So these, and to understand the difference between each one. So some of the important applications of differentiation in calculus are optimization. So optimization is the next thing. So just like we saw in chapter 3, we got to related rates. In this chapter 4, we'll get to optimization problems, in which we are required to find the optimal way of doing something. All right. So if we look at, for example, this graph, and this graph, let's say it stops here and there, then this point 3, 5 is the absolute maximum. That's the highest point for this graph. And if we look at this point 6, 2, it's the absolute minimum, and that's the lowest it gets there, f of 6, 2. Right, so this one is f of 6, 2, and this one f of 3 equal 5. So we can say by definition that the absolute maximum value of f on D or a domain D is when the value of the f of c, for example, f of 3 is 5, f of c is greater than or equal to f of x to any other y value for all the domain. So 5 here, so f of c is equal to a value, and we can find from this picture that f of c is greater than any other y value. Similarly, we can define absolute minimum by having a value on the domain such that less than or equal f of x, corrected that sign there, for all x in D. So similarly for here, f of c, and c here being the 6, if we use that, it's less than or equal than any other y value there. So an absolute maximum or minimum is sometimes called the global maximum or minimum. And we'll look at an example like this. So you can pause the video and go through this example, but we can go to something like this in the homework. And of course, this is an absolute maximum. And you can look at these here. You have also here a maximum, right? If you look at just this interval. But this is not an absolute maximum, it's a local maximum. So note that D of D is the highest point, and A is the lowest point, right? So if we consider only the values of x near B, then f of B is the largest of those, and it can be called the local maximum. So, so if we consider just this, for example, this range, you have something that's increasing, then it's decreasing. It can only do that if you have a local maximum there. So we can describe the local maximum values in a similar way. It just here we say near C. We don't say over the domain. It's not over the domain, but near C value that we compare to, right? And here is a sketch. So for here you have a local minimum. Here you have a local minimum and absolute minimum. So this is the absolute minimum. And let's say the graphs, even if it keeps going here, in this case, it's still gonna be that, but it will have a problem with the maximum. We can say we have an absolute maximum. We can just say we have a local maximum near these 8, or which will be the C value, which in this case is J. So you see you have a local minimum. You also have a local minimum, but it also happens to be an absolute minimum. Here you have a local maximum, because you see the graph keeps going. But in this case, we won't say we have absolute maximum. There isn't an absolute maximum there. So you can check these notes and these details. So for example, here a cosine function, it keeps changing between -1 and 1. So we have local minimum, we have local maximum at various points or various places. And the following theorem gives conditions under which a function is guaranteed to possess an extreme value. All right. And the extreme value theorem says if f is continuous, so there is that condition for this theorem to use, that the function is continuous on a closed interval AB, then f attains an absolute maximum value if f of c and absolute minimum value f of d at some number c and d in interval. So it may not be clear, and we'll explain it as we go through examples, but the conditions are these two. And here the extreme value theorem is illustrated in this example here. These figures. So you have a C here, and you have a, so you have a C1 and a C2. You have a C here, and you have a C here, and these are functions continuous on, of course, closed intervals, A, B, and they attain some extreme values. Note that an extreme value can be taken in more than once, of course. And of course, like in this case, C1 and C2 are local maximum. So let's look at figures 9 and 10. Here, it does not follow it's not continuous, right? This function is not continuous. So we cannot say about it. Also here we have that discontinuity of infinity. So figure 9 and 10 show that the function does not possess extreme values if either hypothesis is omitted from the extreme value theorem. So this function has a minimum value of f2 here, but no maximum value. So we won't say that 3 is a maximum value, because it is not continuous and it does not even reach 3, right? So there is a difference between when we talk limit from left and right, but here to say it's an extreme point using this extreme value theorem, it has to be continuous. If it's not continuous there, then we don't have a maximum value at 3. Similarly for 2, we're not going to say there is an absolute maximum. It's keep going up towards 2. No, it's not continuous there. It is continuous over the domain. However, it rises up. Let's redo. It rises up towards infinity, right? Towards infinity. So once it rises toward infinity, we're not going to say the maximum is 2 or f of 2, right? So that's why there is no maximum there. And here it's open. So notice that this is open. So it's discontinuous. So there is no maximum and no minimum. So the function of whose graph is shown in 9 and 10 on this interval, but has no maximum value. Notice that the range for 0, 3, but this does not contradict the extreme value theorem because f is not continuous. Right. So the function g in 10, similar way, just as I explained it. So this theorem tells us, this extreme value theorem tells that a function has to be continuous to have these extreme values, but it does not tell us how to find them. But if we look at the curves, if you have a maximum, you see the slope is horizontal, which means you expect that first derivative to be 0. So you expect that f prime at c to be 0, at f prime at d to be 0. So that's one idea, and we're going to analyze a little more, right? So it appears that the maximum and minimum points at the tangent lines are horizontal, and therefore they have a slope of 0. So f prime of c and f prime of d are 0. This gives Fermat's theorem if f, but of course we'll see that this theorem needs some work. If f has a local maximum or minimum at c, and f prime of c exists, then f prime of c is 0, which we saw in that picture, right? But now let's look at this example. X cubed. You see here it's flat. The tangent is flat there as well. The derivative is 0, but it has no maximum. You see it's going towards infinity, towards negative infinity. So no maximum and no minimum. Even though Fermat's theorem says that, so it has no maximum and minimum. So the fact that simply means that the curve has a horizontal tangent. Instead of having a maximum and minimum, the curve crosses its horizontal tangent here. So that's the case in this case. So how this is different than the theorem that is mentioned. It's what happens is the curve crosses its tangent, right? So we have that tangent and they cross each other right there, right? So let's look at another case. There is another case, the absolute value, which when we did this, we did continuity, we found that it has a problem coming from left and right. The two values of the limits, left hand, right hand, are not the same. So it can't be found. The function has its local and absolute minimum value at 0, right? But that value cannot be found by using the derivative because f prime of 0 does not exist. And we did in the past because the left-hand limit and right-hand limit are not equal. And you see here, however, there is a local minimum and local max, an absolute minimum at 0. So what's going on? Examples 5 and 6 show that we must be careful when using Fermat's theorem. Example 5 demonstrates that even f prime of c equals 0, there need to be a maximum or a minimum at c. For number 6, there may be an extreme value even if f prime of c does not exist. See, so there may be an extreme value even if f prime of c does not exist. Right, so we need to be careful when we use that Fermat's theorem. So, however, it does suggest that we should at least start looking for extreme values for these number C, where f prime of C does not exist. Such numbers are given a special name where they're called critical number. And we did talk about critical numbers when we looked at inequalities, for example, of polynomials. So if you look somewhere in the notes, we did talk about some critical numbers in the past, even when we did for logarithmic domain. But here is a definition. A critical number of a function f is a number C in the domain of f such that either f prime of C equals 0 or f prime of C does not exist. So this or is inclusive. It means this or that. In terms of critical numbers, Fermat's theorem can be rephrased as follows. So we can rephrase that theorem. If f has a local maximum or minimum at C, then C is a critical number. So now we're talking about critical numbers. To find an absolute maximum or minimum of a continuous function in a closed interval, we note either it is local or it occurs at an endpoint. So the closed interval method to find, which we'll use in some exercises, to find the absolute maximum and minimum values of a continuous, of course, function and some closed interval AB. So closed interval, continuous, right? So number one, find the values of f at the critical numbers of f in AB. Find the values of f at the end point, which means the A and B. The largest of the values from step 1 and 2 is the absolute maximum. The smallest of these values is the absolute minimum. So it's a simple method to